So page 27, a die is rolled 6 times. Find the probability of rolling at least one 4. So we learned that the at least one concept is really just, it just boils down to finding the probability of getting no successes and subtracting it from 1. So probability of at least 1 4 is equal to the 1 minus the probability of getting no 4s. Which expands to probability of getting, I'll use the not symbol here just to make it obvious, but this is really what this is saying is I'm not going to get a 4, so that little tilde is a not symbol. Some people just make them ends, end for not, and that's fine by me. So the first first roll would not be a 4, the second roll would not be a 4, the third, fourth, fifth, and sixth rolls would all not be 4s. Third, fourth, fifth, and sixth. Now the probability of not getting a 4, probability of getting a 4 is 1 out of 6, so the probability of not getting it would be 5 out of 6. It's kind of like a multiple choice question, but with 6 choices. You know, what would be the probability of getting it wrong just by guessing? Well, there's one way to get it right, so everything else would be getting it wrong, right? I want this to happen 6 times, so I raise it to the 6th power. Now for this one, calculator's fine. Actually, surprisingly, we have not used the calculator yet, or I haven't. For this one,
Professor, because I understand you're throwing it 6 times, right? And the probability of not getting, like any of those 6 times, another 4 should be 6, shouldn't it? Because I could throw it 6 times and not get a 4.
You could throw it 6 times and not get any 4s, but the probability of that happening it's pretty remote. So, I mean, just because it's conceivable doesn't mean that it's going to happen. Yeah, because there's a difference between the experimental probability and the theoretical probability. This is addressing the theoretical. Because what this is saying is that we have a 0.665 chance, approximately, because we're going decimal form here. Because even if you math fracket, like converting it to fraction form, the calculator has a hard time with it. But even if you could, it would be such a monstrous fraction that it's not even worth putting it in. So it's about 0.665. And so that's telling me that there is, maybe it's not a great chance, but there's a pretty solid chance that in any 6 trials of rolling a die that a 4 is going to come up at some point. And so I'll just show you a quick simulation. A random integer simulation, and you don't actually have to do this, but I just want to justify it a little bit, because if I do math probability option 5, which is a simulator, the outcomes on a die are 1 to 6, and I want to roll it 6 times. This is just one random trial, but you could see that I got a 4 in there, right? And really, if you think about it, you roll a die 6 times. If a 4 didn't come up, it wouldn't be shocking. But if you had, like, let's say 10 attempts at rolling a die 6 times and a 4 never came up, I think you would be surprised because it should have come up at some point. So here's 1, 2, 3, 4. So in my 4 trials, 2 of them came up with a 4 somewhere. In the 5th trial, I did not get one, so I'm looking at 2 out of 5 trials giving me a 4 somewhere. 3 out of 6, 3 out of 7, 4 out of 7, 4 out of 8, 5 out of 8. Doesn't matter how many times the 4 comes up in my 6 trials. It just has to come up somewhere, right? So I have 4 out of 8, so it seems to be hovering around the 50% mark. 4 out of 9, 5 out of 10, 6 out of 11, 6 out of 12. So it's still hovering around that 50-50 mark. So this 0.665, maybe it's not coming out in my random simulation here, but what the law of large numbers tells us is that if I were to continue doing this process just in each array of 6 values, I'm going to get closer and closer to the true probability. Because again, when I'm looking for at least 1 4, I'm just looking for in my 6 trials for a 4 to come up somewhere. All right, it can come up on the first trial, it can come up on the last trial, it can come up on any of them in between. Now the chances of it happening on every single outcome, that would be shocking. Like that's an example of shocking, a very small probability. Roll a die 6 times and every outcome is the same, that you're starting to wonder what's wrong with the die, right? Because that shouldn't happen. That's like flipping a coin 30 times, and every time you flip it, the result is heads. What's wrong with the coin? That shouldn't happen. But if you flip a coin 30 times and you got, let's say, 7 heads and 23 tails, you'd say, okay, I wasn't expecting that. I don't know is that the coin, or is that just how it worked out? So then you start flipping it more to see if it comes out in the wash, right? So there is a difference between what is like shockingly abnormal and what is like, I didn't see that coming, but I suppose it could happen, all right? That's the difference. Okay, so in one case, you're looking at a probability that should be reasonable, that I didn't see that coming. Something like this would justify that. Shockingly abnormal, you're looking at a probability that's close to 0 or 1, depending on your perspective. Right? So, just things to be mindful of when you're evaluating these probabilities, because again, what are we flipping coins and rolling die and pulling cards from a deck for? This isn't a course on board games. Like we're supposed to learn about probability from these concepts. Okay. So